Hello everyone, and we are on to day 4 of the logarithm unit. We are going to talk today about the number e, the natural log, and how to solve for e based on using the inverse, which is actually called the natural log. So let's even look at what e is first. I say that and you're probably going, that's a letter. It's kind of like pi. Pi is an irrational number, and so is e. E is approximately 2.72, and it's used in modeling. It's used for continuous growth. We're used to talking about growing over a certain time period. E is talking about growing over a time period, but continuously growing, not growing at a certain stage. So E just means it's continuous. So let's look at this. If E is approximately 2.72, so E is approximately 2.72 here. If it says, what is y equals e to the x? Well, another way to write that is y equals 2.72 to the x. Well, if we have 2.72 to the x, this is called an exponential function. We have an exponent, it better be called an exponential function. So right away, we know that 1, which is a quadratic, 4, which is a polynomial, is gone. And then the question is, are we increasing or are we decreasing? Well, 2.72 is greater than 1. We could have written this as 1 plus 1.72. And so therefore, since it's increasing, we know it must be choice 2. And our explanation is what I just said. So let's look at exercise number 2. A population of llamas on a tropical island can be modeled by the equation P equals 500 e to the 0.035 t, where t represents the number of years since the llamas were first introduced. So it says how many llamas were initially introduced at t equals 0. Well, right away we should know this without having to do any math, because the 500 is our initial value. So we should know it should just be 500 llamas. Now why is that? Well, if we have P equals 500 times e to the 0.035 times 0, because t is 0. So we get 500 e to the 0. Anything raised to the 0 power we know goes to 1. So what is 500 times 1? But 500. So our population would be 500 llamas, just like we set up here. Now B, what we don't, it takes a little more work, I should say, is algebraically determine the number of years for the population to reach 600. Well, we know our population better be 600, so we're going to have 600 equals 500 e to the 0.035 t. What's a t? Let's try that again. Well, the first thing that we do, and I stressed this greatly last lesson, is divide this by 500 first. We can't do anything until we get rid of that initial value. So we have 6 divided by 5 equals e to the 0.035 t. And so right now you should be thinking, oh, we have a t, we have a variable in the exponent, and therefore we need to use logarithms. We have nothing else with this, e, so let's look at logarithms. And again, what have we stressed so much over the time is when we have this, we're going to have log base e of 6/5, because that's what it equals. Remember that the log gives us the exponent, so we have 0.035 t. And now I need to divide by 0.035. And so we know t equals log base e of 6/5 divided by 0.035. Well, we take our calculator out and we want a fraction, so alpha y equals enter. To get our log, remember that we go to math, go up to a. Log base e, I always just use this e, remember it's raised to the first power because it's just e, of 6 divided by 5. All over 0.035 or 0.035. You hit enter and we're going to get right around 5.2, and I'm sure it told us what to round to, 1/10 of a year. So we're going to get 5.2 years. So t would be 5.2 years. So that's how long it will take the population for the llamas to reach 600. Now, all that is nice, but writing that log base e is kind of a pain. And so one thing that we can do is the inverse, and it's right at the bottom of your screen here, the inverse of y equals e to the x is ln of x. And the one nice thing of that is, remember that when we take the inverse, it's the opposite, and so that operation kind of goes away. If we take the inverse of e, and I want to show you this right here, if I have here, starting here, if I'm going to take the ln, since ln is the inverse, I want to have you see what happens. When I take the ln and e are inverses of each other, and therefore they're kind of gone. And so I'm left with ln of 6 over 5 equals 0.035t, and divide by 0.035, divide by 0.035. And notice in the calculator what we're going to get. ln, the ln button's right here, ln of 6 divided by 5. I forgot to do fractions, so I'm just going to hit enter. And divide by 0.035. Notice what you get. Get the exact value that we had in the beginning. So when we look at this, the ln function, the natural log function, is the inverse of the e to the x exponential function. It's the inverse of that exponential function with the base e. And so another way we write it is log base e of x. So without using the calculator and using this idea, the log base e of x, let's try exercise 3. We have ln. Well, we know exactly when we see ln, it's equivalent to log base e of x. So we're going to have log base e of e equals, we're going to put in a variable, we're going to say this equals z, we'll say. So we'll go z here. So we always think to ourselves, the logs give us the exponents, so base log, so we have base e raised to the z equals e. And that's really e to the first. So e to what power equals e to the first? So z equals 1. So ln of e equals 1. Let me rewrite that so you can see that clearly. Ln of e equals 1. Let's try this one. Log base e of, we'll call this c. Log base e of 1 equals c. So what does c equal? E to the c equals 1. E to what power equals 1? Well, we said it above in the very beginning of this lesson, that it must be 0. So ln of 1 will always be 0. Let's look at this one, ln of e. Ln of e to the 5th. Ln of e to the 5th. We have log base e of e to the 5th equals what? Well, e to the what equals e to the 5th. Well, we have the same basis, so this must equal 5. And the last one is, how can we rewrite square root? Well, we know that that's equivalent to ln of e to the 1/2. We don't like to write it as square root. We know that square roots are always e to the 1/2. So let's try this again. Log base e of e to the 1/2 equals what? So e to what power equals e to the 1/2? And we know that that must be equivalent to just 1/2. And hopefully what you saw through all of this is that ln of e, when you have ln of e raised to something, the ln and the e are inverse functions of each other, and so therefore you're left with just the exponent. Same thing here, ln of e are inverses of each other, you're left with just the exponent. And when I say inverses of each other, remember what inverses are. The additive inverse of 5 is -5. You're left with 0. The multiplicative inverse of 5 is 1/5. You're left with 1. Okay, same idea here is that the ln and the e are inverses of each other, and you're left with the exponent. So ln of e is 1 because the exponent is 1. Ln of 1 will always be 0. Ln of e to the 5th, you're left with the exponent. So what doesn't change here is that natural logs are the same as logarithms in terms of the properties. And so when we have the ln of x to the 3rd over e to the 2nd, we see division, and so therefore we think quotient rule. So we're left with ln of x cubed minus ln of e squared. The same idea applies for the power rule also. You see a power with a natural log. The key thing is a log, so we still are using the logarithm rules. The 3 comes out in front, so we're left with 3 ln of x. We just stated that ln and e are inverses of each other, and the ln of e squared is only 2, so it's just 3 ln of x minus 2. Choice 3. And let's look at exercise 5, and we'll finish off the day in this lesson with exercise 5. A hot liquid is cooling in a room whose temperature is constant. Its temperature can be modeled by using the exponential function shown below. The temperature T is in degrees Fahrenheit, so we know that this is in degrees Fahrenheit, and is a function of minutes. And notice that we know a liquid doesn't cool at every minute. It doesn't chop down. It cools at a constant rate, so hence that's why we're using E, because E is a continuous rate of change. So it says, with what was the initial temperature of the water at m equals 0? Well, we talked about this at the very beginning. At m equals 0, this whole thing turns to 1. And so therefore, at t of 0, we have 101 plus 67, and that's 108. So we have 108 degrees Fahrenheit. That was the temperature of the liquid at the very beginning. B, how do you interpret the statement T of 60 equals 83.7? Well, we have T of m to equal 101 e blah blah blah. Well, we have T of m to equal this function. So T of m, this is our m and this is our T. So after 60 minutes of cooling, the temperature is 83.7 degrees Fahrenheit. So now we're on to C, which is the part that we're going to be using the actual letter E and the natural logarithm to find it. Using the natural logarithm, determine algebraically when the liquid will reach 100 degrees. So it's that same idea. 100 equals 101 e to the negative 0.03 m plus 67. And just like last lesson, what is the first thing we need to move? Well, we need to move this plus 67 before we do anything. So we're going to get 33 equals 101 e to the negative 0.03 m. And then before we can do anything, we have to get rid of that initial value. We cannot take the natural log until we get rid of this 101. So we'll divide by 101. So we're going to get 33 over 101 equals e to the negative 0.03 m. Now we're at a nice spot. Now we're at a spot where we say, what do we need to do to get this exponent by itself? Because we have the variable and the exponent. So what we're going to do is we're going to take the natural log of each side. Just like we took the logarithm of both sides last lesson, now we're going to take the natural log of both sides. When we take the natural log of both sides, we're going to get ln of 33 over 101 equals, notice that the ln and the e are inverses, we just talked about this, so we're left with negative 0.03 m. The last thing to get m alone is to divide by negative 0.03, and you can use your calculator. I am not going to. I have it already done. M is going to give us 37.3 minutes. And so it'll take 37.3 minutes before, or it'll take 37.3 minutes to reach 100 degrees Fahrenheit. When you see an exponential function that uses e, you must take the natural log. The final question that we will look at today is D on average. As soon as you see the word average, you're thinking slope. How many degrees are lost per minute from 10 minutes to 30 minutes, round to the nearest tenth of a degree? When we do this, we immediately think 10 of 30, change in y, over the change in x. Well, you can use your calculator. Plug this into y1 and go to your table. So if you'd like to do that, do it now. You can pause it. I'm going to just give you the answer because I am assuming that you know how to plug that in your calculator, but you can always check. So t of 30 is 108.1 minus 141.8, and this will be divided by 20, and so we get that it is cooling 1.7 degrees Fahrenheit per minute. Notice that this is negative, so it is cooling, if I can spell, cooling at 1.7 degrees Fahrenheit per minute. It's cooling on average, I should say here. At a rate of 1.7 degrees Fahrenheit per minute. So today we looked at ln and e. If you have any questions, please ask us, and have a good day.